we are going to start our next chapter, that is colligative properties of solution. Now, what is a solution? Solution, as we know, it is a mixture of two or more immiscible or miscible liquids. Now, what we will come to know in this chapter that are types of solutions, a molecular view of the solution process, concentration units, the effect of temperature on solubility, the effect of pressure on solubility of gases, colligative properties of non-electrolyte solutions, colligative properties of electrolyte solutions, and that is colloids. Now, colligative properties of solutions. Solution, a homogeneous mixture of two or more substances, that is known as solution. Solubility, the maximum amount of a solute that will dissolve in a given quantity of solvent at a specific temperature. When solute is introduced into the volume of solvent, the solvent properties change. Means if we introduce solute in a solvent, then the properties of that solvent will change. If we take the example of a salt, if we add a salt in water, the taste and the properties of that water will change automatically. Colligative properties are properties of a solution that depend solely on the number of particles dissolved in the solution. There are four types of colligative properties of solution, that are vapor pressure lowering, boiling point elevation, freezing point diffraction, and osmotic pressure, that is denoted by pi. Okay, here we have denoted it by P1 is equal to x1 P1 0. These are the formulas of vapor pressure lowering. Boiling point elevation has delta TB is equal to KB into M. Freezing point diffraction have delta TF is equals to KF into M. Osmotic pressure pi has pi is equals to nRT. It is also denoted by CRT or VRT or MRT. Okay, there is no confusion about this. Now, vapor pressure lowering occurs with non-volatile substance, that is zero vapor pressure. Non-volatile means zero vapor pressure having substances. Non-ionizing means they does not dissociate. So occurs with non-volatile non-ionizing solutes at low solute concentration, means we are adding it in low concentration. Now this is the glass jar. Here this is the liquid and it gets vaporized in the gaseous form. These are in ordered form and a strong driving force, and this gas is in uh, non-ordered disordered form. Now same over here, if we add solute in this, now here we will observe that there are many particles of gases and here are few particles of gases. This is non-volatile solute and non-ionizing, so it cannot dissociate also, and it has zero vapor pressure, so it cannot change in its gaseous form easily at room temperature. Okay, here are the weak driving forces. Less order. The vapor pressure of a pure solvent drops whenever non-volatile solute is added. Here is larger entropy increase, smaller entropy increase. Okay, now Raoult's law, that is vapor pressure lowering. The vapor pressure P1 of a solvent is directly proportional to the mole fraction x1 of the solvent in the solution. Vapor pressure P1 is directly proportional to mole fraction of solvent x1. Now what is Raoult's law given by? P1 is equals to x1 into P01, where P01 is vapor pressure of a pure solvent. Now x1, the formula is x1 is moles of solvent divided by moles of solvent plus moles of solute, which is also denoted by N. That is, for pure solvent x1 means x1 will be 1 and p1 will be p01, means the vapor pressure of a solvent will be equal to vapor pressure of pure solvent. Okay, p1 is solvent and p01 is pure solvent. Hence this will be given as moles of solute increases, hence x1 will decrease, means mole fraction of solvent will decrease and the vapor pressure of solvent will decrease. As a solute is added, the vapor pressure drops. See, It is given over here. Now P01 the vapor pressure of pure solvent and P1 is the vapor pressure of solution with solute. Hence P1 is equal to X1 into P01. Okay. Hence X1 is equals to moles of solvent divided by moles of solvent plus moles of solute. X2 will be moles of solute divided by moles of solvent plus moles of solute, and X1 will be 1 minus X1. The formula will be like this: P1 is equal to 1 minus X2 into P01. P1 is equals to P01 minus X2 P01. P01 minus P1 will be is equals to X2 P01. Now delta P will be X2 P01. Now calculate the vapor pressure of a solution made by dissolving 218 grams of glucose, which the molar mass of that will be 180.2 gram per mole in 460 ml of water at 30 degrees Celsius. Hence H2 will have pressure that is 31.8 mm per Hg. Assuming the density of the solvent is 100 gram per ml, what is the vapor pressure lowering? Hence P1 is equals to, we have the formula, P1 is equals to X1 into P01, where P01 will be vapor pressure of pure solvent, P1 will be vapor pressure of solution, X1 will be mole fraction of solvent. Okay, now we will come to solution. The vapor pressure of a solution P1 is equals to X1 P01. Now want to calculate, we have to calculate this vapor pressure of solution. What is given? P01, and need to find X1. Okay, first we calculate the number of moles of glucose and water in the solution. Hence N1 of water will be 460 ml into 1 gram divided by 1 ml into 1 mole divided by 18.02 gram, which will give 25.5 mole. N2 of glucose means number of moles of glucose will be 218 gram into 1 mole divided by 180.2 gram, which will give 1.21 mole. The mole fraction of water X1 is given by X1 is equals to N1 upon N1 plus N2. Hence 25.5 mole divided by 25.5 mole plus 1.21 mole. The answer is 0.955. The vapor pressure of water at 30 degrees Celsius is 31.8 mmHg. Therefore, the vapor pressure of a glucose solution is. Now, what is it? P1 we want to calculate, X1 need to find out, and P01 is given. And P1 will be 0.955 into 31.82 mmHg. We have found out this in the previous slide, 0.955. Okay, when we will multiply 30.4 mmHg, finally the vapor pressure lowering delta P is 31.82 minus 30.4 mmHg or 1.4 mmHg, or you could simply use delta P is equals to X2 P01. Now vapor pressure lowering talked about with non-volatile and non-ionizing solute. What about volatile solutes? Solutes with vapor pressure. Examples: ethanol in water. If we add volatile solute in water, then what will happen? Okay, this is gaseous molecules and this is solute molecules. The vapor pressure is equal to the sum of the vapor pressure of the component. The vapor pressure of the solvent is reduced. Now the vapor pressure of the solvent will be reduced. Raoult's law of liquid-liquid mixture. If component A and B of a solution are volatile, Raoult's law still holds. Pa is equals to Xa into P0A, Pb is equals to Xb into P0B. P total will be Pa plus Pb. Hence P total will be Xa into P0A plus Xb into P0B. Assuming it is an ideal solution, for an ideal solution delta H, that is entropy, will be 0. This is illustrated over here. The delta H of solution is equal to delta H1 plus H2 plus H3 in this step A, and this one is B step. Step 1 delta H1, delta H2 and delta H3. This is a solution. These are the solutes. Ideally, if solvent solute interaction will equal to solute solute plus solvent solvent. interaction. Raoult's law, benzene and toluene from an ideal solution, benzene A and toluene will be P. Okay, this will be the pressure graph of toluene and benzene, which will be represented in this way. Benzene and toluene similar structures, similar forces, dispersion forces. What about other liquid-liquid mixture? Now, what about liquid-liquid mixture? These are both have a similar structure. Raoult's law of liquid. Most solutions are non-ideal and deviate from Raoult's law. Force, that is AB will be smaller than force of AA plus BB. See, positive deviations, we have given the graph over here, and this is the negative deviation. A and B hate each other and want to get out. And here in second, A and B like each other and want to stay together in this way. Solutions and cooking. Now this is a question. Adding salt, that is non-volatile solute, to water solvent will, first one, reduce the time it takes to heat up, make the water boil hotter. Now solutions and cooking, we have given it in Raoult's law. P1 is equal to x1 into P01. As we have illustrated further, then moles of solute, if we add moles of solute over here, if we increase the moles of solute, then what will happen, that mole fraction of solvent will decrease and vapor pressure of the solution will decrease, but boiling point will increase. Okay, here we have given the graphical representation. Pure solvent is in green line, solution is in red line. This is the difference between the pure solvent and solution of boiling point, and this is TB, that is temperature, TB pure solvent, and TB of solution. This is delta TB. Temperature, the graph is vapor pressure of solvent, torr, versus temperature. Okay, as a solute is added, the vapor pressure decreases, more energy, means higher boiling point is required for vapor pressure to equal atmospheric pressure. And boiling point elevation we will see now. As expected from Raoult's law, which predicts lower vapor pressure, boiling temperature elevation is determined by number of moles of solute dissolved in solution. Change in boiling point temperature delta Tb is directly proportional to molality of the solution, which is m. Hence it is given by delta Tb is equals to Kb into m. Delta Tb is the change in boiling point degree Celsius, m is molality of the solution, mole per kg, Kb is boiling point elevation constant, which is given degree Celsius per mole or per kg or degree Celsius into m. Note, the Kb value only depends on the solvent. The molality m depends only on the concentration of solute. Now, we have asked a question, solution and cooking. Adding salt, that is non-volatile solute, to water solvent will make the water boil hotter, reduce the time it takes to heat up. What the answer will be? The boiling point of water increases from 100 degrees Celsius to 102 degrees Celsius upon adding of salt. Then what will be the answer? The answer is make the water boil hotter. Now these are the freezing point depression examples. Over here it is snow, or we call ice, and the fourth one image is, these are the friends which keep you in freezing mode. Non-volatile solutes, these are non-volatile solutes which remain close or intact to you. They lower your freezing point, means if you are angry, they will lower your freezing point, means they will make you cool and calm. Freezing point depression, adding of non-volatile solute to a solution lowers the freezing point of solution relative to pure solvent. Change in freezing temperature, that is theta Tb, will be directly proportional to molality of solution m. This is the formula delta Tf is equals to Kf into m. Delta Tf, the change in freezing or melting point degree Celsius. M will be molality of solutions and Kf will be freezing point diffraction constant. Note, the Kf value only depends on the solvent. The molality M depends on the concentration of solute. Now this is the phase diagram of solution versus water. This is at 1 atmospheric pressure. The pressure versus temperature plot is this, graph is plotted. This is solid ice and liquid water. This is vapor form. These are the three forms of water. H2O, which is given. This is over here, it is the point of freezing point of solution, and this one is freezing point of water. This is boiling point of water and boiling point of solution. Boiling point elevation is given over here and freezing point diffraction is given over here. Now these are the freezing point diffraction, boiling point elevations of some molecules, that is water, benzene, ethanol, acetic acid, cyclohexanes. Now colligative properties of solution, as we discussed earlier, it is a review, that is solution solubility definitions are over here. These are the freezing point depression and boiling point elevation constants of some molecule. Now we will calculate ethylene glycol, that is CH2OH. CH2OH is a common automobile antifreeze. It is water soluble and fairly non-volatile. It is non-volatile solute. Calculate the freezing point of solution containing 651 gram of substance in 2505 gram of water. The molar mass of ethylene glycol is 62.01 gram. Now how we will find delta Tf? We have the formula, delta Tf is equals to Kf into m. Okay, now what we want to calculate delta Tf, and we have constant Kf and need to find m. Thus, to solve for the molality of the solution, we need to know the number of moles of ethylene glycol and the mass of the solvent in kilograms. And 651 multiplied by 1 mole, 62.01 will give 10.5. This, following this formula, we have calculated that at end 4.91 m we will get. Now we find the molar mass of ethylene glycol and convert the mass of the solvent to 2.505 kg and calculate the molality as follows. We have calculated and substituted this formula from the table. Kf 1.86 degrees Celsius per mole. Therefore delta Tf is equals to Kf into m. We will substitute the formula because pure water freezes at 0 degrees Celsius. The solution will freeze at m 7.79 degree Celsius. Now, what is osmosis? Osmosis is a selective passage of solvent molecules through a porous membrane from a dilute solution to a more concentrated one. A semi-permeable membrane allows the passage of solvent molecules but blocks the passage of a solute molecules. This is 3% salt solution, selectively permeable membrane we have attached over here, and this is distilled water. Salt solution is rising. Okay, solution stops rising when weight of the column equals to osmotic pressure. This is alternative view. This is high pressure. This is solvent solution. Net transfer of solvent. Time more out than in, less out than in. Okay, a semi-permeable membrane allows the passage of solvent molecules but blocks the passage of the solute molecules. Now osmosis. We have again described it in more view, that is pure solvent, and this is solution, this is semi-permeable membrane. Now the pure solvent will travel into the solution. This molecule, higher vapor pressure will be travel to lower vapor. Osmotic pressure will increase. Okay. Osmotic pressure pi is the pressure required to stop osmosis. What is osmotic pressure? Osmotic pressure is a rate controlled phenomenon. The solvent is passing from the dilute solution into the concentrated solution at a faster rate than in opposite direction, that is establishing an equilibrium. The osmotic pressure is denoted by pi is equal to CRT, or it is also denoted by nRT, where pi is equal to osmotic pressure, C is molar concentration of solution, R is 0.0821 atmospheric per mole Kelvin, T is absolute temperature K. The average osmotic pressure of seawater measured in the kind of apparatus shown below is about 30 atmospheric pressure at 25 degrees Celsius. Calculate the molar concentration of an aqueous solution of sucrose. Pi is equals to CRT is the formula. Now we have the solution. C is equals to, we have to find out the concentration. Pi is equals to RT, and 30 atmospheric pressure, we have substituted the values over here, and we have given 1.23 m. M means that is concentration only. I have denoted it by m. A solution is prepared by dissolving 35.0 gram of hemoglobin. This is the question asked over here, and we have the formula pi is equals to CRT. We have pi, R and T, and we have to find C. Okay, first we will calculate the molarity. So this is concentration which is denoted in molarity. The volume of the solution is 1 liter, so it must contain 5.38 into 10 raised to minus 4 mole of Hb. We used to use this quantity to calculate molar mass. Now we have calculated the molar mass, that is 6.51 into 10 raised to 4 gram per mole. Now reverse osmosis. What is reverse osmosis? Here it is water, it is semi-permeable membrane, and water molecules pass through the semi-permeable membrane to dilute the brine solution from higher concentration to lower concentration. As we have seen that in general the drinking water are nowadays are of RO, that is reverse osmosis. Our water is impure, that it contains higher amount of solute particles. A semi-permeable membrane is attached over it, and we get a lower concentration of water, that is pure water. Now this is until the height of the solution creates sufficient pressure to stop the net flow. Second one is osmotic pressure. Now applied force over here. Reverse osmosis is the application of an external pressure in excess of osmotic pressure to force water molecules to the pure water side. Okay, used worldwide to purify seawater. FT Myers FL gets its drinking water from the Gulf of the Mexico using reverse osmosis. US Navy submarine do as well. Dialysis is another examples of this phenomena. Now colligative properties of non-electrolyte solution. We have seen the electrolyte solutions. Now it is non-electrolyte solutions. The formulas are same, but I have denoted here M regarding C. Colligative properties of electrolyte solutions. Colligative properties are properties that depends only on the number of solutes particles in the solution. Sucrose 1 molar dissolved 1 particle M, NaCl 2 molar, FeCl 334 m, hence Van 't Hoff factor I will be given as actual number of particles in solutions after dissociation, number of formula units initially dissolved in solution. Okay. Now the boiling point elevation will be IKB into M, IKF into M, and IMRT, which will also be denoted as ICRT. What if the solute doesn't dissolve completely? Solution homogeneous mixture and suspension heterogeneous mixture. If the solute doesn't dissolve completely in the solution, then colloids will be formed, which have the particles of range from 1 to 1000 nanometer, that is 10 raised to minus 9 to 10 raised to minus 6 meter. Now what are colloids? Colloids are the dispersions of particles of one substance throughout a dispersion medium of another substance. In contrast to suspensions, the particles in colloid do not settle out of the solution, but they make the solution cloudy. Typical colloid particle size is 1 to 1000 nanometer. Large particle size colloid, that is translucent, cloudy and milky. Small particle size colloids can be clear. Small particle size means colloidal solutions will be excess of sugar solution. or cloudy means the fog. These are the examples of colloids. Now these are dispersion mediums and these are dispersed phase. These are the names. If there is gas as dispersion medium and dispersed phase is liquid, the name will be aerosol and example will be fog and mist. If the dispersion medium is gas, dispersed phase is solid, then also it is aerosol, but the example will be smoke. Now, if we will consider liquid phase and solid as dispersed medium, then it will be sol and example will be milk or magnesia. Now, soaps and are also in colloids, but they are surfactants. Soaps are surfactants that are surface active agents, have a hydrophobic part and a hydrophilic part. Soaps and detergents are important examples of colloids, which are these are non-polar and this is polar. And this is hydrophobic head and hydrophobic tail and hydrophilic head. Okay, this is water polar. This is grease like non-polar substance. See, the hydrophobic tail is inside it and hydrophilic is outside inside the water. Sorry, the hydrophilic head is inside the water and the tail is outside the water, like this one. This is a colloidal solution. The Tyndall effect. Colloids scatter light when it shined upon them. That's why we see the sunlight scattered by dust. This is also why we use low beams on cars when driving in fog. This is the Tyndall effect. Okay. Now we have come to the end of our chapter.